I'm very excited to introduce Andrea Baishi, who I first met at this RSS, also with Dieter there. And although it was COVID, I think we had a good time. And I'm really excited to welcome Andrea here at UW, even if virtually. So Andrea is a PhD candidate at UC Berkeley in the Electrical Engineering and Computer Science department. She did her undergrad at the University of Maryland and has worked at NVIDIA Research and Max Planck Institute. Andrea studies safe human-robot interaction, and I especially like how she brings people into this domain to inform and test algorithms. I also want to say that she's in the academic job market. So with that being said, I now welcome Andrea.
Thank you so much for that nice introduction. Yeah, so today I'm going to be talking a bit about my work on bridging safety and learning in human-robot interaction. So in my research, I develop robots that interact with people. This includes autonomous cars driving around human-driven cars, quadcopters flying nearby pedestrians, or assistive robots helping out in the home. Now, in all these domains, in order to effectively interact with humans, robots need to learn from and about people. For example, consider a quadrotor here, which is navigating around my lab mate Sylvia. However, the quadrotor here isn't sure where Sylvia is going to move, and so it's not sure how to behave around her without colliding into her. In scenarios like these, the robot can use a learned predictive model and infer where Sylvia may be going by observing her behavior. Seeing Sylvia take a step forward allows the robot to update its model and predict that she's going straight to the door, after which the robot plans a path to avoid her and make its way across the room without colliding into her. Now, unfortunately, the robot's learned model won't always be perfect because human behavior is vastly complex, varying between individuals, environments, and over time. For example, we spilled some coffee in Sylvia's path here, causing her to want to take a wider path around this area. However, the robot's learned model never saw this kind of data a priori. In fact, the robot's sensors may even be unable to detect this kind of coffee spill. And this causes the robot to mistakenly predict that Sylvia will move forward, when in fact, she's actually going to be deviating and taking this wider path. In scenarios like these, when the robot's learning goes wrong, it can lead the robot to confidently plan unsafe decisions. As Sylvia moves around the coffee spill, the robot ends up colliding with her head on because it's relying on this incorrect model. And so there's this tension that we have a lot in human-robot interaction, where robots need to learn about people in order to effectively interact with them, but these robots also need to be safe. And so broadly speaking, I've been really fascinated by this challenge of how we can ensure safety in human-robot interaction, particularly when robots are learning from or about people. Now, my approach is influenced by my work in control theory. And control theory has a long history of enabling us to formally study how dynamical systems, like robots, evolve as a function of their control inputs. Classical physics-based control theory has enabled robots like drones to safely avoid colliding with obstacles, airplanes to fly reliably despite external disturbances like wind, and robots to ensure that they don't fall down and actually reach their goals. However, safe robot behavior gets a lot more challenging with a human in the environment too. And this is because now we can't just study the evolution of the robot's physical state over time, but we also have to consider the evolution of the human state too. And when people move, people don't move completely randomly. People actually have some internal policy that really maps from the state that they observe into their human actions. So here this policy is denoted by pi theta, and theta are the parameters of this policy which really drive how the humans make decisions. The problem is that the robot doesn't know how the human's policy works. It doesn't really know what that is a priori, and so it doesn't know how the person's going to move in the future. And this poses a real safety challenge for the robot when it's planning around the person. However, this is where learning can come into play. The robot can actually observe the human's behavior, for example, that step that Sylvia took forward, and use this human data to learn about the human's policy. Here, the robot updates its estimate of the policy parameters and then plans its best motion in light of this update. However, when robots are learning from humans, it's not just physical states that are evolving, but also the robot's learning is evolving too. And so thus safety must really take into account both how the human and robot will move and interact, but also the limitations of what the robot could possibly learn. And to capture this really complex interplay, a core idea in my work is to treat robot learning algorithms as dynamical systems that are controlled by human data. With this idea, we can develop new control theoretic methods for ensuring safety when robots interact with and learn from people. So throughout my PhD, I've studied how to formalize safety in human-robot interaction through a variety of research directions. This ranged from investigating how robots can learn from human data, to how we can efficiently compute safe sets and safety controllers, to the intersection of safety and robot learning from humans. And it's exactly this intersection of learned human models and safety that I really want to focus on today. So today's talk is going to focus on the core of my thesis, which was on ensuring human safety in the robot navigation domain. I'm going to talk about two very related projects. The first is how we can imbue a sense of confidence awareness into robot planning. And then secondly, how we can formalize safety analysis and online learning from human data. In both of these works, I'm also going to touch a little bit on the implications of this work and how it can generalize to broader domains. All right, so let's begin by taking a closer look at robot planning around people. So for this part of the talk, I'm going to use a running example of a quadrotor navigating indoors around a pedestrian. To plan its own behavior, the robot needs a model of the human's motion. One model I've worked a lot with throughout my PhD is this noisily rational model of human behavior. This model has roots in econometrics and cognitive science, but has also been widely used throughout the robotics and inverse reinforcement learning communities. Under this model, the human chooses their actions UH based on their current state XH and an additional parameter theta, which captures the human's intent. A very simple example of this intent could be that the human wants to move towards the door. Under this probabilistic model, the human's actions won't always be optimal, but an action will be exponentially more likely the more efficient it is for the human's intent, captured here by the state action value Q. Now, typically these possible intents and in fact the Q function come from offline learning. We can use a corpus of human motion data to learn possible salient aspects of human decision-making. For example, on the left is a heat map showing salient locations that people walk to indoors, or on the right, we see maneuvers people often make on a highway. In a running example, our possible intents are going to be the door, table, and chairs, denoted here by theta 1, 2, and 3. If we condition the human model on the door, the distribution places exponentially more probability mass on the human moving forwards than backwards. If we condition on the table, we see the distribution shift pointing towards the table, and conditioned on the chair, we see a new distribution that predicts the human's going to go left. Now, since the robot doesn't know a priori which of these intents a specific person has, the robot can actually maintain uncertainty over these intent parameters, visualized here by this belief distribution. At deployment time, the robot's going to observe how the human actually behaves and infer the human's intent online from these observations via, for example, this Bayesian update. So here, the robot has incorporated this measurement, and it predicts with 70% certainty that the human is going to the door. And as a result, the human state predictions indicate highest likelihood of the human leaving the room. Collision checking against these predictions, the robot then plans its own motion to stay away from the human and get to its goal. So these models prove very useful in practice. In fact, here we're going to see this deployed in hardware. On the left, you see a third-person view, and on the right, you see a top-down view of a quadrotor using this noisily rational model to predict where Sylvia will walk. The predictions are shown as these distributions that are emanating from her body. And as we run this video, we're going to see that as Sylvia walks straight towards the door, the robot infers this, the predicted behavior matches what she does, and the robot can safely make its way across the room. All right. Unfortunately, people don't always behave according to our learned models. For instance, if a bee flies into the room, the human will suddenly start running around in an erratic way that was never seen before at training time, and therefore is not predicted by the human model, causing the robot to crash. In fact, I would argue that if I released bees into your room right now, It is unclear if even I, as a human, could predict how you are going to behave. Now, we wanted to test this out in our lab, and although we didn't have bees, we did have that coffee spill, which we put right in Sylvia's way. Now, this coffee spill is going to cause Sylvia to deviate, and because the robot doesn't know about this aspect of her intent, the human model is going to fail to predict this behavior. So as she deviates, the predictive model is consistently incorrect, and it results in a collision between Sylvia and the robot that we saw earlier in this talk. So what really went wrong here? Well, we know that the robot had this prior over intents that it possibly knew about: the table, the chair, the doors. After observing the human move away from the coffee spill, the robot tried to update its belief over these intents. But the problem is that the robot cannot correctly update its belief because none of the modeled intents explains the human's behavior. And this is because its model is fundamentally misspecified and missing the hypothesis that the human is avoiding the coffee spill. In other words, no matter how the learning algorithm evolves, it can never explain the human data well. So what can we do to mitigate this? Well, if we revisit our human model, we can see that it assumes that people behave approximately rationally. That is, they take actions to approximately optimize their objectives. In fact, there's this built-in parameter, beta, which is typically set equal to 1, and it governs how optimally the human is expected to behave under the modeled intent. Just to remind ourselves, this rationality assumption induces this peaky distribution over human actions. But if the person moves around the coffee spill, which the robot doesn't know about, the human will appear as irrational under all of the robot's modeled intents. And so here we had this idea where if the human's actions at runtime appear irrational under the model, then this is actually an indication that the robot has a misspecified model of the human. And so the key idea here was, instead of a priori fixing a value of human rationality, to instead explicitly treat rationality as an unobserved time-varying parameter of the human model. Then, by enabling the robot to estimate human rationality online, this beta parameter can be interpreted as a principled measure of model confidence, or the degree to which the human model explains the human's current behavior. Concretely, the robot is going to be maintaining a belief over possible values of beta. And here's a little caricature of the prior over model confidence values from low confidence to high confidence. After observing the human take a step forward, the robot uses that belief update to try to update its belief over model confidence. But how does this belief update really work? Well, allowing beta to vary from low to high actually induces a spectrum of human models. The lowest value of beta, equal to 0, corresponds to a uniform distribution over all human actions. As we increase beta, we're going to make that distribution peakier and peakier, placing almost all probability mass on the optimal action for a given intent. The belief update is comparing how likely the observed data is under each of these models. And in this case, determines that the model with high beta, in other words, our high confidence model, best explains this data because it places the most probability mass on it. So we see that model confidence shift. And now what's going to happen is when the robot predicts the human's behavior, it automatically has the robot rely more on that data-driven structure that we encoded because the robot is confident in its model. Interestingly, now when the human runs away from the unmodeled coffee spill, the robot's going to perform that same belief update again, but this time when the robot's comparing the likelihood of the human running away, this data vector I'm showing you here in yellow, under each of these possible beta models, it's going to discover that actually the beta equals 0 model, which uses a uniform distribution over human actions, best predicts this data. And so this automatically means that the Bayesian inference infers low model confidence. And what's really exciting here is that as the robot's model confidence drops, the predictive model relies less and less on the modeled structure and predicts more and more irrational human behaviors. In fact, In the limit, when the robot loses all confidence, the predictions will account for all possible human behavior with equal probability. If we bring in insights from control theory, we can see how these predictions are automatically converging to the human's forward reachable set, or the set of all states the human could possibly reach via their dynamics and regardless of their intent. Using the forward reachable set, the robot safeguards against all possible, including worst case human behavior. But what's particularly beautiful here is that we aren't hand tuning when we worry about these worst case scenarios. The predictive model automatically adjusts its conservativeness by simply observing the human data. So let's see what this looks like in hardware in our running example with the coffee spill. Pay attention to the predictions visualized in the video to the right. While Sylvia moves straight, the predictions are confident, but as she deviates from the model by stepping around the coffee, the confidence drops and the predictions automatically blow up to account for more irrational behaviors. But when she returns to walking directly to the goal, the model confidence increases and the distribution tightens. Let's take a look at another scenario. Here, the two red dots indicate modeled intents in the room, and the dashed circle is a third unmodeled intent. So first, let's see what happens when we always trust our learned model and just use a fixed confidence predictor. As long as the person walks towards one of these red dots, the predictions effectively capture the behavior. But when the person walks towards the unmodeled goal, the predictions are systematically wrong, predicting the person will turn around and run back towards one of the modeled intents. And this ends up resulting in a collision between the human and robot. In contrast, with our Bayesian model confidence, the predictions look confident while the human's moving towards the goal, but smoothly and automatically shift to the forward reachable set when the human starts walking towards the unmodeled goal. And so by relying on our confidence-aware model, the robot automatically plans a wider path here around the human to stay safe. There's a lot more that we've investigated when we are talking about confidence-aware models, from looking into this approach in the self-driving car domain, to connections with forward reachable sets, to providing probabilistic safety assurances on the likelihood of the human and robot colliding. And you can find more details on all of this in our IGRR paper. So now that we've taken this deep dive into confidence-aware human models, let's take a closer look at the exciting implications and generalizations of this idea. So an outstanding challenge in human-robot interaction is having robots interact with multiple humans. But predicting how multiple people behave quickly becomes intractable. For example, if predicting one human requires updating 1,000 states, then 2 humans requires 1,000,000, 3 requires 1,000,000,000, and so on. And although some modeling assumptions might alleviate this complexity, they will inevitably introduce systematic prediction errors. By using confidence-aware models, though, we can still deploy simplified interaction models with confidence. For example, we can treat each human as behaving independent of the next. Under this assumption, standard predictive models would tell us that the humans will pass through each other, which clearly physically can't happen. But we can leverage the idea of model confidence here by reasoning about the observed behavior as deviations from these simplified tractable models to still enable safe and scalable multi-human, multi-robot interaction. Here is a hardware example with 2 quadrotors that are navigating around 2 people. The robots are going to be predicting both humans without any knowledge of how people interact with each other. Or in fact, that my labmate Jaime in the lower left of the screen is going to be dancing the entire time he's moving through the space. As the humans start to interact with each other in the center of the room, you'll notice that the predictions automatically become uncertain, causing the robots to briefly hover in place until the interaction ends. Ultimately, all the robots avoid collision and make it to their goals despite relying on simplified interaction models of people. So far we've seen how this idea of having the robot estimate model confidence can help in the pedestrian prediction domain with quadrotors. However, I've also demonstrated the utility of this idea in the autonomous driving domain. On the right, there's an example of how we can deal with unmodeled potholes, for example, on the road, or on the left with dealing with unmodeled game theoretic interactions that arise in autonomous driving. Additionally, I've also investigated this in the inverse reinforcement learning domain, where a robot needs to determine if it can learn effectively from human input. It's also been really exciting to see this idea be used and extended by others in the robotics community to automatically generate failure scenarios for stress testing, as well as for monitoring user expertise and collaborative tasks. I think a large reason why this idea has proven so useful is because inferring model confidence as captured by the scalar beta parameter is a principled, tractable measure of model confidence, and it automatically enables downstream robot decision-making to adapt. Okay, so now we have robots that can modulate their level of confidence and automatically adapt their behavior based on how trustworthy their models are. Let's take a closer look at what safety questions still remain. So from before, we know that our robot can automatically monitor its confidence online, smoothly shifting its predictions from intent-driven to worst-case conservative. But if we take a closer look at these videos, we will actually see that it takes some time and several observations for the robot to adapt its model. For example, when the person steps around the coffee spill, it takes several observations to increase uncertainty. Or in the unmodeled goal scenario, the human needs to take a few steps before the robot actually shifts to the full forward reachable set. And this really begs the question, can this cause safety issues for the robot downstream? The fact that it takes some non-trivial amount of time to adapt the model. And in fact, it can. So consider this simple motivating example where an autonomous car is at an intersection and it's inferring if the human is walking across the sidewalk. The robot sees the human move forward and it's going to infer that it has a high model confidence because all it knows about is that people like to cross the street and the person actually started crossing the street. And so because of this high confidence that it's inferred, the robot predicts that the human is going to continue to move forward. And so the robot decides to accelerate through the intersection. However, as the person changes their mind and turns around, there actually isn't enough time for the robot to collect enough data and detect that its model is wrong. In these few moments, the robot's model is still adapting to the data it's seeing, but the robot has committed to unsafely accelerating, resulting in a collision. We can take a look at this in simulation here. At the start, the human is predicted to only move to the right with that confidence-aware predictor. But note, as the human moves backwards, it takes some time for the predictions to become conservative, but during this time, the robot's already committed to accelerating through the intersection, after which it's too late for the robot to stop. So the question that really needs answering here is, can the robot somehow anticipate how quickly it could lose confidence and use this anticipation to plan a safer path? More broadly, this question is actually part of a broad set of previously ignored safety-related questions for robots that rely on online learning algorithms. Specifically, these questions include things like, what's the fastest time it could take the robot to learn its model parameters? Or, what initializations should the robot use so that we can guarantee that the robot learns the correct parameters, regardless of what they might be, and a finite number of observations? Or finally, what's the worst case time it can take the robot to learn the correct model parameters, whatever they may be? Now, these questions are actually really natural to start answering once we go back to that core idea of treating robot learning algorithms as dynamical systems. Now, just like when we were using control theory to study the safety and evolution of classic physics-based robot state, we can now develop new optimal control methods to answer our safety questions, but about these actual learning algorithms. So let's work through an example of how to set up such an optimal control problem. If we return back to our original running example, let's try to answer the question, what is the fastest time it could take the robot to detect that its model is misspecified? In other words, what's the fastest the robot's belief could go from inferring high model confidence to low model confidence? So to start answering this question, we need to keep track of two quantities: where the person is physically, as well as the robot's belief over model confidence. So the first step in our framework is to define the joint state space Z, which includes the human physical state XH, and the parameter estimate, which in our particular example here is going to be that belief over the parameter beta. Now, augmenting the state with the estimate is akin to representations you may have seen in POMDP or adaptive control methods. Next, we need to keep track of how the human's physical state and the robot's belief evolve over time. Now here, the human's control actions drive the evolution of both the physical state and the estimate. Thus, our joint dynamics are going to be represented by this function f, which evolves the joint state z based on the actions the robot observes the human take, uh. We can expand out these dynamics to see how they're simply the stacked physical dynamics and the learning dynamics. And when you see these learning dynamics here denoted by f sub L, remember in our scenario, this is just that Bayesian update, which is a function of the prior belief you had, the current human state, and the current human action. Now that we have this new dynamical system, we can start to formalize our question that we had up here at the top. Specifically, what we want to do is understand how the robot's high confidence belief can evolve to a low confidence belief. In other words, detecting that its model is wrong. Although the dynamics characterize how this system evolves, we still need to solve for this question of how much time is it going to take and which human data steer us to this final state. However, we can actually formulate an optimal control problem whose solution is going to exactly capture the answer to these two questions. So since we're interested in knowing the fastest time, our optimal control objective is to find a minimum final time t. Since the human's action sequence is the data the robot observes, it will be our decision variable here. We also have a few constraints in our problem. First, we need to enforce the joint dynamics over this entire time horizon. We also need to ensure that the joint system starts from a given initial condition. So in our running example, we have this initial condition where the human is halfway across the crosswalk and we have a high confidence estimate. Finally, we need to ensure that our system actually detects that its human model is misspecified. For example, our target belief might be to say, well, we want 95% probability mass on a low value of beta. We will encode this as part of our constraints via this belief B star, which is the desired belief that our system should achieve at the end of this time horizon, big T. Then we'll measure the distance between our desired belief and the belief our system achieves at the final time. So the belief we achieve at the final time is denoted here by B superscript T. And this constraint requires that the robot needs to be epsilon close to detecting its model is wrong at the final time. Overall, what we have just posed here is a minimum time optimal control problem. But what makes this somewhat challenging is this terminal time constraint. However, what's really exciting here is that this is actually an instance of a reachability problem, which determines if a certain state is reachable from a given initial state of the system. However, this is actually a novel reachability problem over beliefs that evolve via the human data, which to date has not been studied before. Now, during my PhD, I've worked on and advanced a class of reachability tools called Hamilton-Jacobi reachability, which can handle general nonlinear dynamics, single and multiplayer settings, and can flexibly represent various constraints. At the high level, our solution method is going to leverage the principle of dynamic programming to actually solve this optimal control problem. Now, given that optimization problem, we can crunch some numbers, do some math, and derive this dynamic programming backup. Now, for those of you who are familiar with the standard Bellman equation used in MDPs, this is similar to the standard Bellman equation, but with a few key differences. These differences include things like we have a discount factor equal to 1, we have a requirement of a specific initialization of our value function, denoted here by this blue L of z, and over time, we have this additional minimization with L of z, which essentially keeps track of our constraint and ensures it's satisfied. Pictorially, what we're doing really here is we initialize our value function at the final time with the signed distance function, L of z, which measures how close our joint system is to the terminal constraint. For example, all beliefs that have greater than or equal to 95% probability mass on the low model confidence satisfy our terminal constraint and are therefore assigned a negative value by L of z. Then we propagate these values over time, just like dynamic programming tells us we need to, while at each time step, keeping track of our constraint encoded in L of z. Ultimately, like any other dynamic programming problem, we're going to obtain a value function v, which is defined over all possible initial conditions. Intuitively, this value function captures the minimum time it will take to detect that the robot's model is misspecified, starting from an initial joint state z init. So what we can do here is plug in our specific initial condition in this example of the human halfway across the street and the robot having high model confidence, and extract the fastest time to detect model misspecification or that inferred low model confidence. So that t fast is exactly capturing the answer to that question. So going back to our motivating question, we just saw how the robot can automatically anticipate how quickly it could lose confidence. Let's see how we can actually leverage this anticipation to plan a safe but efficient path. So recall our intersection example. If the robot was only betting on the fact that the human will continue to cross, then it would plan that sharp acceleration path. So here the path goes from the initial time to the final planning horizon of 4 seconds. Alternatively, if the robot was only conservative and it didn't trust its model, it would plan to wait at this intersection for 4 seconds. Now, only doing the blue plan is overly conservative, and committing to the red plan before the robot has certainty in this event can cause safety violations. Instead, one way for the robot to deal with this is to generate something called a contingency plan. The premise of contingency planning is that the robot only has to be conservative for a short period of time by anticipating when it will have certainty in the future. So in our scenario here, before the robot has certainty, it's going to plan an initial conservative trajectory, shown here in white, that safeguards against all possible human behaviors, the four reachable set. At some future time tb, the robot anticipates it will be certain about its model, and the robot creates one contingency plan for each possible outcome. Here we see the red trajectory in the event the model confidently predicts the human, and the blue trajectory in the event the robot detects low model confidence. However, the overall safety of this plan really hinges on an appropriate choice of that time tb. Because if tb is too short, the robot will still be uncertain and unable to safely commit to a contingency plan. But if tb is too high, the robot is going to be too conservative and risks just sitting at the intersection the entire time horizon. So how can the robot effectively choose this principled branching time that balances safety and efficiency? Well, the optimal control problem that we just posed and solved automatically gives us a principled answer to this problem. The robot anticipated when it will lose model confidence in the future, and it can confidently choose this branching time for its planner. If we take a look at a simulation, the same portions of the plan are visualized here, with white being the safe initial plan, blue being the plan in the case the human behaves in an unmodeled way, and red in the case the human continues across the intersection. The branching time here is set to be equal to 0.45 seconds, which is exactly that t fast we computed via our optimal control framework. In this scenario, when the person changes their mind and moves back across the intersection in an unexpected way, the robot only slowly inches forward and doesn't actually slam on the gas, preserving safety with the human. In the alternative scenario, though, where the person continues to behave in a modeled way, the robot can still confidently rely on its contingency plan to first inch forward and then accelerate through the intersection. This ability to make a safe and efficient decision in such a tricky scenario really comes down to the robot being able to anticipate in a principled way how its model can change online and actively accounting for this during planning. So we just saw how this novel belief-based reachability framework can facilitate safety analysis when robots learn online from human data. Let's talk a little bit about what this implies and how we can generalize. So earlier I outlined the space of possible new safety questions. In fact, we solved one of these together. We just computed the fastest time to lose model confidence and used it to make a safer robot motion plan. However, we can actually use the same exact formulation by Hamilton-Jacobi reachability and answer other questions like how should we initialize our learning algorithms and what would be the slowest time to learn. In particular, the beauty of this reachability framework I proposed earlier is that it's agnostic to the dynamics of the robot learning. It enables a range of belief-based constraints to be encoded within the same formulation, and it can be applied to a variety of human-robot interaction settings. For example, we can gain insights on environments that are really challenging for intent inference. Or we can design safe but efficient motion planners via the worst case time to learn in these difficult intersection scenarios. Or we can generate automatically legible and deceptive human data and behaviors. Finally, we can also determine effective initializations for gradient-based learning. So now that we've taken this deep look into how robots can safely navigate around people, even if their learned models are misspecified, and if these models take non-trivial amount of time to update. But what I want to do now is take a moment to step back and look at what interaction looks like beyond navigation. More broadly, I want to talk a bit about what I'm excited about investigating in future work. So all of us are familiar with human-to-human interaction. And when humans interact, we aren't always avoiding collisions with each other. In fact, physical interaction with another person is really useful. For example, children naturally learn how to do complex tasks like cutting vegetables or making a salad by being physically guided by an adult. So I was really interested also in this interaction paradigm during my PhD, and I wanted to get robots to learn from physical interactions like these too. So in this example, the robot is moving a cup from the shelf down to the table for my lab mate Ellis. And the robot has a preconceived notion of how to do this task where it keeps its end effector high above the table. But much like adults supervising the children, Ellis actually wants the robot to keep the cup close to the table. And so in this line of my research, I developed robot learning algorithms, which enable Ellis to physically correct the robot during task execution. And from this physical interaction, the robot learns to keep the cup close to the table. But so far, our notion of safety was a traditional one. It was one that said safety means avoid physical collision. But here we actually wanted to have the human physically interact, because when the human could come into contact with the robot, it was not just safe, but it was also desirable for learning. And so close human-robot interaction really demands more than just collision avoidance definitions of safety. And so this has gotten me really interested in the question of what is the right notion of safety in these nuanced human-robot interaction problems. So to start making some progress, let's take a look at a concrete example. So here we're back in the physical interaction domain, and the person is trying to teach the robot to hold the cup closer to the table. However, in this scenario, what's going to happen is the robot's going to consistently misinterpret the human's correction. And what's going to happen is as the human keeps trying to give feedback to the robot actually incorrectly learns to hold the coffee mug at an angle instead of learning to keep its end effector close to the table. And so not only does this result in jerky miscoordination, but the robot has ended up with an incorrect understanding of the task. And so here we're already seeing possibilities for new notions of safety, like, is the robot aligned with the human objectives? Or maybe safety means here that we can prevent unintended learning on the robot's part when getting feedback from the human. These are just small parts of new notions of safety that we should be able to capture when robots collaborate closely with people. And so to better understand the question of what safety can mean, let's break down the space of problems related to safety, learning, and human-robot interaction into 3 axes. So far, we've seen a lot of collision avoidance scenarios throughout this talk. However, there's a whole spectrum of interaction, all the way up to physical collaboration like we just saw. This axis really describes the space of how the robot is interacting with the human and directly affects our definition of what safe should mean. Secondly, in all these contexts, the robot is learning. The learning can happen via low-dimensional models or via complex function approximators. And third, there's this question of how to perform safety assessment. This can happen on 2 extremes: offline, where the human model and the robot decision-making are stress tested, to online, where the robot continuously monitors its interaction with the human. In my thesis work that you saw today, I've primarily been looking at safety in the collision avoidance scenarios with low-dimensional human models. However, there's a rich space of safety questions that I'm really excited about investigating, which expand along the dimensions of interaction and learning complexity. I want to highlight just a few directions that I'm particularly excited about. So inspired by my work on physical and human robot interaction, I'm really excited to develop novel formalisms for safety in collaborative learning settings. So here, safety analysis would enable robots to, for example, assess which data to learn from, for example, teaching human inputs, and which human data to ignore, for example, adversarial human inputs. Furthermore, even when the robot is not physically interacting with humans, we still lack a deep understanding of how humans and robots learn from each other. This is especially critical in settings like autonomous driving, where human drivers will repeatedly interact with and learn about autonomous cars, or in caretaking contexts where people are adapting and learning about a robot over time. And so my perspective here on treating learning algorithms as dynamical systems opens up really exciting connections to game theory, which rigorously couples the influence between the human, robot, and their respective objectives. And this can really advance safety in HRI by, for example, ensuring that when humans and robots learn from each other, they're learning in stable and desirable ways. Finally, safe human-robot interaction should ultimately account for the robot's perception capabilities, state space representations, and dynamics. I'm really excited about developing robot algorithms, which can effectively learn to interact with humans in a perception-aware way, to, for example, enable robots to actively and efficiently query humans for supervisory input to, for example, augment their understanding of the world. To me, all these exciting directions on safe human-robot interaction are really enabled by formally treating robot learning algorithms as dynamical systems that are driven by human data. And with this perspective, we can automatically start to synthesize safe robot interaction with people when we have learning in the loop. With that, I'd like to thank you and thank all my wonderful collaborators, and I'm happy to take any questions in the chat or in person. Thank you.
Thank you so much, Andrea. I invite anyone to, just clap hands also, but we have a question in the chat and you can continue dropping them or even interrupting here. So I'm just going to read it for you. It's from Carolina, and she mentions she doesn't have a mic, so I'm just going to read it. Do you assume that the human is aware that is helping the robot learning? And this is about the initial part of your work when she dropped the question. She also says, I'm thinking that the robot is assuming that the human is a cooperative agent. I mean, that is going to behave as it's supposed to be.
Exactly. So you're absolutely correct. In the work that you saw with the physical interaction, we were assuming that the human input that the robot gets is helpful. It is something that the robot should be learning from. So you can think of the human here as like a teacher, and that's an assumption under which the algorithm works. But similarly to what I was mentioning at the end of my talk, I think there's some really exciting things that we need to start thinking about when maybe humans aren't always in a teaching setting. Maybe they're suboptimal teachers. Maybe they're explicitly adversarial. I see this all the time when I run demos, especially with children who come to our lab. I do this physical interaction robot demo, and they always try to mess the robot up. They always try to make the robot learn the wrong thing. So definitely not an assumption that necessarily holds for all people, which is why we need to go back to the drawing board and really think about what's the right notion of like a human model and what's the right way to make the robot learn in really robust ways. Any other questions for me?
Yes, there is one more. In your experience, what is the performance of solving HGPDE in real time, particularly for the case when the robot needs to adapt model uncertainty within 0.45 seconds?
Yeah, that's a great question. So as you saw in the talk, the version of the reachability formulation I had here was in discrete time, but in general, there's also a continuous time version of it, which is called the Hamilton-Jacobi-Bellman PDE. Now, whether it's in discrete time or continuous time, both of them are solved by dynamic programming, which means that they can be really, really computationally intensive to solve, which means that typically if you're solving the full dynamic programming problem, you're most likely to be doing a big offline analysis. And then you basically let the robot have this big lookup table that it's carrying with it around. And then it can just basically do, O of 1 lookup to figure out whether or not it's safe. If you're doing online adaptation or something's changing about the formulation of your optimal control problem, I've actually worked on those kind of settings as well. And there's several things that you can do to make this PDE solution faster. one of which, and I'm happy to link to you, you did this paper from my CDC paper from 2018, where what we really did was we tried to come up with a local update algorithm that basically spends a lot of computational effort only on regions of the PD that are really changing and keep the other ones fixed. And this really allowed us to get a lot of performance speedups. And I can link you to that paper so you can take a look at some of the runtime comparisons, specifically in MATLAB. And even in MATLAB, we were seeing a lot of really promising results. We also have a C++ version of solving these HJPDEs, which is only even more fast. And then if you add on top of this all of the GPU accelerations that you can get, it gets even faster. So I can definitely chat with you a little bit more and also send you some references if you're interested in runtimes of these kind of problems. Let me actually, I'll pull it up in the chat while we are talking.
Maybe I can ask one question. First of all, yeah, great talk. Really nice work, Andrea. I was wondering, could you say a bit more about how you represent states in these cases? For example, from the car, like the state of the pedestrian, what do you include in that state? Because there's multiple goals a person can go to, there's which direction you're facing, all these different things. And it seems like, did you represent it often as a grid state space, or what is it that you're using there?
Yeah, and the examples you saw, it's the predictions, for example, of the human or the human action model was represented via, let's say, like XY or XY theta state space representation, which was gridded for computational reasons. In general, these models don't require you to do that, but that was what we did for these methods. And in general, I think richer notions of state is exactly what I think we should be thinking about going forward, beyond just XY theta. There might be other notions of state that are really important. Like, for example, if you look at people's gaze, that's a really important indication of like how people are going to be behaving, or facial expression, you know, et cetera, et cetera.
There is an interesting question in the chat. So chat says, I had a tech issue near the end, so sorry if I missed it, but is there room to consider that not all collisions are equally bad? It might be advantageous to be close and increase the probability of collision if the consequences of the collision are reduced. And I think you kind of touched it, but would love to hear more.
Yes, so actually this is a really, really great question. And actually I know that Karen is on the call right now. So Karen and I worked together at NVIDIA several months ago, and we have a paper out recently on sort of talking about how you can richly encode a lot of different kinds of notions of safety into these kind of reachability-based frameworks that I talked about today. And you're absolutely right. So one example that we like to give is think about when you're driving autonomously, or when you have an autonomous car, a collision that's, for example, side by side, where both cars are facing forwards and they hit like this, is significantly less worse than like a T-bone collision that is a lot more fatal. And so maybe you want to prevent both, right? You don't want your car to hit from the side or hit in a T-bone, but you definitely can have a sort of ordered ranking of which of them are more bad and which of them are less bad. And that can perhaps let your system make more like efficient or effective maneuvers while also preserving safety, but understands which of these kinds of collisions are more or less worse. We're just treating all of them as like equally bad. So I think there's a lot of work to be done there. We just started thinking about that, and I'm sure you could talk to Karen more about this, and I can also share our archive preprint related to these kind of questions.
Great. I would like to add a question on the safety part. So you mentioned several ways where safety could be defined according also to your problems. Is there any other way to define safety for you that you haven't addressed so far, but you would be interested in expanding?
Yeah, so I think when I was talking in the future work section about what safety can possibly mean when you have a robot and a human learning from each other, I think one notion of safety might be whether or not the human and the robot can converge to an understanding of each other's intents. So if both agents are learning, like the robot's learning about the human, human's learning about the robot, can you show that like the two agents will be actually able to converge to a good understanding of each other? And this depends a lot on how they interact, how they behave. and certain behaviors and interactions, leak more information to the other agent and make you more or less confident about what the other agent wants to do. And so perhaps a notion of safety there that I haven't studied so far is maybe more from a stability or convergence perspective. Like, can all agents converge to understanding each other effectively in a short period of time? And that's something I haven't studied so far, but I think a lot of the tools that I described here are nicely amenable to starting to answer these kind of questions too.
And just as a follow-up, is there any advantage for it to be for a short period of time?
Oh, I didn't say specific. Okay, so, okay. I think the time horizon or like number of interactions you need could be beneficial in some contexts. For example, sometimes when people prove like convergence properties of algorithms, it's like asymptotic or exponential. And like maybe you don't have that much time to be interacting with another agent. And so you want to have that learning be like really, really effective and only require maybe a few rounds to stabilize and to understand each person's intent, so that going forward, you just can basically act really, really effectively. It's almost like when you get put into like a new team with a bunch of new people, you want to figure out what are everyone's objectives and what is everyone really good at as fast as possible, so your team can be really effective at doing the task. If that takes you a really long time to converge to an understanding and converge to some kind of like good team dynamic, I would argue it's like going to be a strictly less efficient team. So there's a notion of like converging quickly in maybe a number of time steps, or a similar kind of notion of fastest time to converge here that could be valuable.
Yeah, that makes sense. On the other side, could be valuable for a longer period if we're talking about a task that throughout that process, people are learning more than just to get to the same goal, like a learning task, right? You're actually learning something while you're also converging to something together.
Yeah, that's true.
Yeah.
No, I think there's a lot of questions that we still haven't, like we've only started scratching the surface of, and I like what you were mentioning here, because that's also really interesting.
So I would like to take this opportunity to thank Andrea again, and I invite everyone to do the same. This was a very, very good talk, and we'll look forward to see where you're going next, and good luck for everything.
Thank you.
And
so
thank
much.
you everyone for being here.
Thank you. It was great to be here.